So before talking about this Huiskin and Illmann's proof of this inequality, I need to show some monotonicity formula under the inverse mean curvature flow, as if the isoparametric difference was monotone under the mean curvature flow or the curve shortening flow. So there are many concepts of mass in general relativity. And one of them is so-called Hawking's quasi-local mass. So it measures if my M is some surface which bounds region omega, then this Hawking mass of this surface is kind of mass bounded by this surface. So it's a kind of mass of omega. And it is defined by this quantity here. Of course, it's very hard to understand the meaning of this, but what we can what we can imagine is, if you remember the Willmore inequality, then h squared, if I integrate for two spheres, for two surfaces, I always get it's greater than 60 pi. But that's for a Euclidean space. If my space is like the universe, which we assume here as a non-negative, three manifold with non-negative scalar curvature, then this is usually we can make this less than 16 pi, and the difference exactly measures how much the space is curved, and after some scaling given by this quantity here, we define some notion of mass. That's the Hawking mass. And the important monotonicity observed by Garrosh is that if my surface is connected and the ambient manifold, three manifold, has non-negative scalar curvature, then this Hawking mass is non-decreasing. So it's, so the DDT of this Hawking mass is non-negative. So, of course, when I say it's non-negative, I mean, if I flow this initial M by the inverse mean curvature flow, I skipped the huge assumption. If I flow this by inverse mean curvature flow, then the Hawking mass is monotone increasing. So let me show you this. So DDT of the Hawking mass, if I compute the derivative, the derivative can fall in the first factor. Then I get this. And then it can also fall into the second factor. Then I get this. So our goal, since we want to show it's non-negative, we want to show the derivative of integral of h squared is less than this term here. So let me compute the derivative of integral of h squared. Then we want to first compute the evolution of mean curvature, which I just give you here. It's actually very similar to the stability operator in the minimal surface, because it's like the first variation of h, which is the second variation of area. And we also know what is the derivative of the volume form. So since here I have volume form here, if I compute the derivative, I have one term some terms coming from the derivative of h squared here, and the other terms that comes from the derivative of volume form times the original h squared. And we'd like to show that, yeah, we would like to estimate this. So to make this non-negative scalar curvature assumption, we modify as the following. So by the Gauss equation, the intrinsic Riemannian curvature tensor has this relation by ambient curvature tensor and the second fundamental form. So this explains the Gaussian curvature of my two surface has this relation. So my lambda 1 and lambda 2 is the principal curvatures of this M. So lambda 1 and lambda 2 can be written like this. Moreover, the scalar curvature can be written like this. So in total, my minus 2 ambient Ricci of in the direction of nu can be written like this. It's just a manipulation, yeah, algebraic manipulation. So if I plug in this to this evolution computed in star, I get this. Now I use the Gauss-Bonnet here. And then here, the integral of this term, if I apply the divergence theorem, I got this. So now from here to here, I used two things. First, I assumed my MT is connected. So yeah, the Euler characteristic is less than or equal to 2. Moreover, this is non-negative, so I can throw this out. And yeah, I use three things. So, and then the assumption was this ambient scalar curvature is non-negative. So using that, I got this. And another manipulation says this a squared, which is lambda 1 squared plus lambda 2 squared, is just equal to this term here. Finally, I threw out this. Then that explains the desired inequality. So we showed the monotonicity of Hawking mass under the assumption that there is a smooth solution to the inverse mean curvature flow, and MT is connected, and then what is it? And then the ambient manifold has non-negative scalar curvature. So the next thing is how do we use this monotonicity formula to prove the Riemannian panels inequality? We start from explaining what is the mass in general relativity, so-called what is the ADM mass. So the usual setting in general relativity is this asymptotically flat 3 manifold. So this manifold is 3 manifold, which is complete, but sometimes it has a boundary. And outside of some compact set, so there is some compact set K, and if we think the remainder, then it's diffeomorphic to this R3 minus R ball. And the metric on this R3 minus ball is very close to the Euclidean metric. So here is the Euclidean metric here, and here is the error. And the error decays very fast with order r to power minus of tau. And tau now is assumed to be greater than 1/2. And yeah, so my extra remainder decays, and its derivatives also decays with the same order. Under this assumption, there's some notion of total mass of this system, which is called the ADM mass. This is the name of 3 persons. They define the mass in this kind of limit of Fox integral. So yeah, it's very complicated definition, but I won't use the definition today. So what's important here is this ADM mass depends on the definition depends on this parametrization chart phi. But it's actually independent of that. So it's a kind of geometric invariant. Okay. An important question now is whether this ADM mass is positive or non-negative, and that's famous theorem, the positive mass theorem, which was proven by Shen and Yao, and later by another way by Witten. And one important example of this asymptotically flat manifold is Schwarzschild metric, which describes some rotationally symmetric Ladier solution. Ladier the symmetric metric space. So it's given by R3 minus the origin with the metric conformal to Euclidean space. So we can compute and see the following things. First of all, the R equals to m/2 is totally geodesic. In particular, it's a minimal surface, and it's called the apparent horizon. So it's there's some history on that, but the way I understood is some kind of outermost surface that you cannot come back after you move through this surface. And yeah, I think there are many other articles that explains this background. And the next thing is, what is the area of this totally geodesic sphere? That's easy to compute. You just plug in x equals to m/2 and find the area. That's 16 pi times m squared. And you can compute. You can see that there's no compact minimal surface outside of this outermost. This outside of totally geodesic sphere. So that's why I said this is an outermost minimal surface. Moreover, we use this definition of ADM mass and compute directly to see the ADM mass of this Schwarzschild metric is equal to this parameter m. That's why we denote this by small m. Okay. So then let me first state the Riemannian Penrose inequality. Actually, there is more general Penrose inequality, which is still very open question. And this is some special case of that. which could be written only in terms of Riemannian geometry. So suppose my M3G bar is an asymptotically flat three-manifold with a negative scalar curvature, and it has a boundary M0. So we could draw like this. This is three-manifold. There is some boundary. This 0, this. And another assumption, this is the outermost minimal surface, in the sense that there's no other compact minimal surface in M bar other than this boundary. So the physical interpretation situation is there's some black hole here inside of this M0, the boundary. So what you can observe is what is the area of this M0. So black hole make some horizon, and as we see from this Schwarzschild metric, if M is large, the area becomes large. So there's some, to make this horizon, it has to make some influence in the whole space and should increase the total mass. So so the inequality says the ADM mass has to be at least to this quantity on the right hand side. And as you see from the previous slides, the equality happened for the Schwarzschild metric. Yeah, so the Riemannian Penrose inequality is to show this, and equality holds if and not, and also equality holds if and only if, for the Schwarzschild. So there is a heuristic proof of this inequality which uses the inverse mean curvature flow. So this was observed by, I think, two physicists, by Zhang and Wald. So another assumption we need in this proof is if M0 is connected. Yeah, suppose initial surface, which is the boundary of my three manifold, is connected minimal surface, and I can flow the inverse mean curvature flow, say like this. So it becomes large and large. So it will exhaust our whole three manifold. One may ask how a inverse mean curvature flow could exist from this minimal surface, because minimal surface means my speed is infinite, but actually by perturbing your surface a little bit, you can show, there is some solution starting from minimal surface. Assuming that the solution exists, smooth solution exists for all time, we know the monotonicity of this Hawking mass. We just saw that in the last lecture. So the later Hawking mass is bounded below by the initial Hawking mass. And this initial Hawking mass, because it's minimal surface, this term is 0. So we immediately get the right-hand side of the Riemannian Penrose inequality. Moreover, they observed, we believe this inverse mean curvature flow, as time goes to infinite, it becomes round and round. So it becomes like a round sphere in the round sphere. Then they could show this Hawking mass actually converges to the ADM mass. So if we accept this observation and this assumption that M0 is connected and smooth solution exists, then collecting this all together, so ADM mass has to be greater than the initial Hawking mass, and that's the Riemannian-Penrose inequality. Okay, so that's a heuristic proof. And what Huiskin and Ilmanen did is to remove the assumption that the existence of smooth solution. So they couldn't remove this condition that the M0 should be connected. So if M0 has several components, they could show this inequality, but this term here is replaced by the area of the largest component. And that's why their theorem is called Riemannian-Penrose inequality for a single black hole case. And later this was proven by Hugh Bray for general cases. So let me consider how they define the weak solution. So weak solution they defined as the Church defined the level set solution. So the inverse mean curvature flow, if we define it using level set method, then it's a degenerate elliptic equation of this form. So here is my M3 manifold. If this is my initial region, and this is my initial surface, M0, then of course the arrival time at this initial surface is 0. And as it moves, every point outside of initial region omega 0 will be passed by our solution MT. So we can record its arrival time. So here, for instance, this point on MT has arrival time equal to T. If we collect all these things, U solves this equation. Okay, so this solution exists whenever my initial surface is outward area minimizing. Okay, area minimizing and mean convex. To be more correct, even if without outward area minimizing condition it exists. Okay, so what is the outward area minimizing condition? So it means my region MT at each time minimize the outside area, but the competitor is just something that contains my omega t. So of all other possible regions which contains this omega t, this boundary of omega t has the least area. That's what we call the omega t is outward area minimizing. And some of the important property of this weak solution is the solution is outward area minimizing at each time. Moreover, this weak solution still satisfies this exponential growth of area. By the way, one typical singular behavior of this weak solution is it could happen that your solution at some time, say t minus epsilon, could be looked like this, but immediately at mt, it can jump. So some point, some region immediately jumps. So your surface is not moving continuously, but has some jump like this. And it actually satisfies some variational equation, but I won't go in that direction. Oh yeah, so the brief idea, this was written in some article. So the brief idea of why this weak solution also preserve this monotonicity of Hawking mass is the following. Suppose my solution is not smooth and has a jump. Then I want to show still my weak solution satisfies the monotonicity of Hawking mass. Remember, the Hawking mass is given by this. So through the jump, the outside area, since my t doesn't change, outside area is just the same. But if we view this surfaces before and after jump, this new surface should have h equals to 0. If otherwise, you can vary this surface a little bit to make the area smaller. So that means your surface is no longer outward area minimizing. So okay, so that means this integral of h squared decrease, because previously I had this region, but now this is replaced by some region which is minimal. So yeah, so through the jump, this term becomes smaller, so whole mass becomes larger. So that's the idea of in this monotonicity formula. Why this monotonicity holds for the weak solutions as well. So that's just the idea, and they did Huiskin and Ilmanen proved this in a rigorous way, and that proves the Riemannian-Penrose inequality. Okay. Now we want to move on to the last, and I think the most interesting topic of this talk. So I want to relate this isoparametric inequality and this ADMS. So this is given, this is observed by Huiskin and other people. So I told you that if my ambient space is positively curved, I can put more mass, more volume, more volume than the Euclidean space. I told that somewhere in my first talk. So the idea is, if space has non-negative scalar curvature and if it has some boundary, which is the horizon, then by this effect, we could put more volume for given area. And that additional volume will have some relation with my mass. To see this relation, the one important example is the following. Let's think of the Schwarzschild metric of mass m, as I mentioned here, as I mentioned before, like this. And we compute for given area A, so the question is like this. If I give some number A, what would be the largest volume that a surface of area A could contain in this Schwarzschild metric space, Schwarzschild manifold? Of course, yeah, among those, the surface that contains this outermost area, outermost minimal surface. Actually, the answer is this ball centered at the origin maximize this volume. This is called the isoparametric profile. So if we compute that, so the area has to be at least greater than 16 pi times m squared. And we directly compute, so given area, we can compute the corresponding radius of this ball. So let me draw this situation here. So here's the origin. Here is the outermost minimal surface. And for given A, so for given A, you first find the corresponding R that has the boundary area of A. Then we compute the volume between the horizon and this ball. So that's given as the definition of isoparametric profile phi m of A. Then I didn't compute in this slide, but what we obtain is this expansion here. As A increase, your R will increase. And since my manifold is asymptotically flat, asymptotically close to Euclidean, we can expect that the volume should be first close to the volume of Euclidean ball. So that's here. Remember, yeah, this is the C2 that I computed in the first part. And the important thing is this. In addition to this Euclidean volume, the additional amount is given by this 1/2m times A. There are some lower order terms. So it exactly suggests that my m allow me to put more mass in given area. More volume in given area. So this suggests another definition of mass. So this is given by, this definition is given by the Huiskin. So I just solve this equation in terms of m. That's this expression here. So you compute lim suv of this additional quantity for all sequence of omega that exhausts my total space M3, M bar, yeah, M bar. course, if you see the definition, there's another condition that this omega has to be outward area minimizing. But I will skip that part. Okay. Yeah, so this is a new definition of mass. So I will denote this by M iso. Then the theorem of Huiskin, which is unpublished, is that for asymptotically flat manifold, this M iso defined by this expression is equal to the ADM mass. So ADM mass could be characterized by this isoparametric difference. So it says, yeah, I just explain you again. So this term in Euclidean space cannot be positive. But since I'm on a asymptotically flat 3 manifold of non-negative scalar curvature, I can put more volume than this. So I measured the difference and divide by some scaling factor, and that characterize how much mass was contained in the original space. So I think Huiskin gave some talks on this result in many different places, and you can even find his talk in YouTube. So that's a very nice reference. But this result was unpublished. But later, some rigorous proof was given by these two people, and later these four people gave different methods and showed the same theorem. So I think they are both good reference. Okay, the proof of this theorem rely on this key observation here. And I want to say, so the theorem states like that: if MT is the solution to the mean curvature flow, and if I know the Hawking mass has uniform bounds by M prime, then I can think of the function, isoparametric profile function. Then this A sub t computed, isoparametric profile computed that A sub t minus Vt is decreasing, and I would say that is very close to our computation for the isoparametric inequality. So if you remember, in the proof of isoparametric inequality, we first assumed the Willmore inequality. I put this lambda, but this was some definite number given by the ball. Then, under this assumption, we showed this difference is is monotone decreasing, and we needed, of course, additional condition that it converges to zero, but that was a crucial thing. Now, similarly, we assumed Hawking mass is less than M prime. If you remember the definition of Hawking mass, this means my integral of h squared is greater than some number. Then under that assumption, I'm showing some quantities decreasing, and this first quantity, if you remember what my phi M prime is, this is like 1 over 6 square root of pi L3 over 2 plus 1 over 2 M prime. M prime L plus lower orders. So at its first dominating term, it's very, it's just the same as the isoparametric difference, but we have something extra. So I won't compute this, but yeah, we can similarly show this is decreasing. Moreover, they have to show this is decreasing for weak solution. Then using this by manipulating the monotonicity of this quantity, I can rewrite this monotonicity like this. Yeah, it's just if you take these two out, then it's just a rearrange of the monotonicity formula. Then suppose I start from some very large coordinate sphere. Suppose my M0 is some very large surface, which is asymptotic to a coordinate sphere. And then I flow this by the mean curvature flow. Then I have this monotonicity. And after very long time, I can assume that my V is smaller than some finite number small v. Then we are then we leave at this point. We conclude this, and if I divide by say in order to derive m iso, if you remember the definition, I should divide by the area. So you divide both sides by 1 over area, 2 over area. Then this small v over a vanishes because I assume v is finite. So this proves one side m iso less than m prime, and and the other side is easier. So I will not talk about this. Yeah. So the thing is, we can use the mean curvature flow and the inverse mean curvature flow to characterize the ADMS in terms of this some information about this isoparametric inequality. Oh yeah, before talking about other things, let me just mention something. So one huge importance of this M iso is we can define this mass in terms of C0 information of our metric, Riemannian metric. Instead of, but in the case of ADMS, to compute the flux, my G has to be smooth. But we can reconstruct the same result using C0 definitions. So that could be used to define or show some identities on mass for very rough space. Okay, so that's and let me just finish this geometric inequalities by introducing other inequalities that has been shown using the inverse mean curvature flow. So yeah, the first one I mentioned this earlier. So Guan and Lee showed the Minkowski inequality for non-convex hypersurface, and that was the mean convex star-shaped hypersurface. And Simon Brandot, Hong, and Wang showed the Minkowski inequality for another space, say anti-de Sitter Schwarzschild metric space. And there are others. One could show Penrose type inequality for other asymptotically hyperbolic space, or even we can show the Alexandrov-Fencher inequality that is some generalization of Minkowski inequality for Rn or other ambient spaces. Yeah, for this one, one uses the not only the inverse mean convergent flow, but some other expanding flows of some other curvature function. But methods are very similar. Find some monotone quantity and then investigate where it converges. Then you can recover the desired inequality from that.